Hello everybody, welcome to another episode of Learning Happy Hour. I'm your host Mitch Densley, Jason Yates is with me as well, and I got a good friend, Shakti Kumar here with us. And Shakti, what is this hieroglyphic you've drawn here? I don't understand this. What are we looking at?
So we're going to talk about how the Palo Alto Networks firewall does decryption, which is something a lot of people want to know. So we basically will go through basics of how SSL handshake happens first to get an idea of what SSL handshake is and how the data gets encrypted and transferred over. And then we'll talk about how the firewall handles that SSL handshake and does the proxy.
Nice. And that's all this.
Yeah, that's what we're going to learn today.
I can't wait to see how this pans out. Awesome. Well, show us.
Like Mitch and Jason talked about that, we're going to discuss SSL decryption. But before we start decryption, we need to understand how the SSL handshake itself works. That gives an insight of how decryption is even possible. So we'll take a scenario where we have a PC and we call this as a client. And this client wants to talk to the server, which could be anywhere in the internet. And we can just give any random server. Let's call the server name as panw.com. Now, one of the common aspects of an SSL is basically it's a tunneling protocol. But as a tunneling protocol, we need to have encryption for sure, but we also need to have authentication, and we need to also be able to verify. So we do hashing. So one of the methods in which the SSL handshake makes the data secure and authenticated and verifies the integrity is called certificates. And so I'm going to take an example of a certificate. Let's say there is a root CA. It could be any public root CA. We can have an intermediate root CA. And let's say this certificate is signed by this chain panw.com as one of the leaf certificates which we get. So leaf certificates is the end certificate which cannot sign more certificates. That's why I do not have CA at the end. CA is the one which is a certificate authority which can sign more certificates if allowed by its signer. So panw.com. Now whenever we have a certificate is a big container in a way, and it has a lot of attributes inside. Out of many attributes we have things like common name, SAN, and other aspects, but two more things we have in a certificate is keys, and we call them public key or private key. Now key pair of public and private is available in other protocols also, for example SSH. When we do SSH handshake, there is also a public private key which gets exchanged, but there is no certificate to exchange, so the keys get directly exchanged. In this case, the certificate exchanges that public key, so I'm going to create public and private two names I'm going to use there. So I'll say this panw.com has a public and a private key. So I'm going to say pub pub and pvt as private. I'm intentionally using red and green colors because I will be using them for hashing encryption, so it makes more sense. Now, because we're doing SSL and we know SSL uses TCP, I'm assuming the three-way handshake is already completed, and I'm going to straight away start with the client hello. So the first message between the client and the server would be a client hello message. Now in the client hello, there are a lot of other information which gets exchanged, but the most common or the most important message we are going to talk about is ciphers. Now cipher is a set of algorithms for encryption, hashing, and it's basically a suite, and the client can decide to send how many ciphers it wants to talk about. So the client can say we support 16 ciphers. So it's basically declaring that I, as a browser or as an agent, is capable of supporting 16 ciphers if the server wants to use any of those ciphers. Other informations apart from ciphers are like the TLS version we are using and a lot of other things. What we're trying to understand is the main concept which will make us understand the decryption or the forward proxy here. So ciphers being sent to the server will choose one of the ciphers and reply back. So one selected cipher. Apart from the cipher, the server needs to give a server certificate. Now the server certificate has two objectives. The first objective is the certificate itself, which is used to identify the server so that the client can trust the server if this is a trusted destination I need to connect to. The other objective of the server certificate is the public key which goes inside the certificate. So we're going to talk about both of them. Another thing we need to understand is basically the certificate store which we have on the client. A certificate store is basically a store where the client knows what are the trusted certificate authorities and certificates which the client can trust. It could be a browser based, it could be the operating system like Windows or Mac can have their own certificate stores. The certificate store is important because this is what decides if the client can trust the server, and we typically expect either the root or the intermediate CAs to be part of the certificate store here. So we can have a root CA or we can have the intermediate CA here. If either of them are present on the client and when the server cert comes in, the client here understands that the panw.com is a trusted certificate. Again, not to go into the details, I'm going to just take the certificates here and let's say we have panw.com and this carries the public key inside. So I'm emphasizing public key because that's what we are going to talk more about. The public key which goes into this, it does not carry private key ever. The public key is the only key which is sent to the client. The private key is never shared. It remains on the server. When the client receives this certificate, and I'm also going to again do public here with the public key. The next thing the client needs to do is create a shared secret key, or I call it pre-shared key or PSK. So the client needs to first generate a PSK, or like I said, it's a pre-shared key. When the pre-shared key is generated, the public key which we receive from the server is basically encrypting the PSK, and then this PSK file is sent to the server. So when the server receives the pre-shared key which was encrypted by the public key sent by of its own, it uses the private key to decrypt it. And we basically get the pre-shared key. So this is one way of what we call it as symmetric and asymmetric keys. So PSK here is the symmetric key which was created through asymmetric keys. So we use the asymmetric key of public and private to exchange the asymmetric key or a pre-shared key in this case. So both the client and the server have the same key right now. What they need to do is to generate a master secret key, but this key is basically calculated by both of them separately. So let me use another color for that, and I'm going to say calculate. And I call it MSK or master secret key. Also, some people also call it shared secret key or session key. There are different names, or session ID. It's basically one final key or the ID which will be used to encrypt and decrypt between the client in future. So let's do the same thing here where we use the PSK to calculate the MSK or the master secret key. By the way, the PSK is not the only factor which is used to create the master secret key. Again, not to go into the details, but remember the ciphers which we exchanged, those ciphers are also a factor to generate the master secret key. So it's not just the PSK, but the ciphers, and there are other factors, there are other random things which are used to make it more random so that it cannot be easily calculated by man in the middle. Now that both the client and the server have this master secret key, this key will technically be used to exchange any data between them. So if the client wants to send the data, it is going to encrypt this data with the same master secret key. I'm going to say encrypt here. When the server receives this data, the server can use the same key to decrypt it. And then we can have the data here. Similarly, when the server needs to now send another data, it can use the same master secret key, send it over to the client, and client can use the same master secret key to decrypt that data. And this is why we call the master secret key, or like I said, the shared secret key or the session key as the symmetric key. We use a asymmetric key, public and private, via the certificate to generate or calculate a master secret key, which will be now used for encryption and decryption between the client and the server. So now that we have a fair idea of how the SSL handshake works in terms of the keys we use and the certificates, now let's talk about decryption. So why do we need decryption? And I'm pretty sure most of the folks already are aware decryption is important, because if the firewall cannot see what's going through the tunnel, there is no way we can protect. So it's basically like a secured tunnel to send threats through the firewall. So decryption is important again, and we'll try to understand how can decryption work. If it's so secure, how are we doing decryption? Now, the idea of decryption is to become a man in the middle, and we also call it a proxy. A proxy term is used where the firewall, or any device for that matter, gets a packet and decides to create a new packet for that packet. And that's when we call it proxy, because I'm proxying for something. So let's try to create a setup which I had there. I might draw a little small now. So let's say we have a client now. Now, let's draw the server somewhere here. And we're going to take the same example of panw.com server. And let's assume that we have the same hierarchy, so I don't have to write it again. So pan.com is signed by an intermediate CA, which in turn is signed by a root CA. Now, in this case, you're assuming there is a firewall in between. And let's say this is one of our firewalls, PA220. I like it. Small and awesome firewall. So we have a client, we have a firewall, and we have a server at the end. Now, the firewall could be anywhere in the network. And we'll talk about why the position of the firewall does matter when we do the decryption. Okay. What we're going to now talk about is when your own trusted network wants to go to the internet. Then that's when we call it as forward proxy, because we already trust the firewall which is going to do proxy for us. But we are trying to do proxy because firewall wants to protect for the contents which we receive from the server. Because we do not trust the server, but we do trust the firewall. In that situation, we call it as forward proxy or outbound decryption. So in an outbound decryption, again, like we talked about, there will be a three-way handshake. I'm going to skip the three-way handshake, and we'll start directly with client hello. So let's assume the client is sending a client hello to the server again. I'm going to now use abbreviated word CH because we have a little less space now. And let's assume we have the same 16 ciphers being sent. I'm going to skip the version and other stuff for now. Yes, TLS version and everything else will also be shared with the server. Now, when the firewall receives this packet, a client hello packet, it needs to decide if it can decrypt. And we do need a decryption policy which will check that. Now, decryption policy lookup happens if we are familiar with the life of packet in the app ID stage, where we do a decryption lookup and the firewall realizes that this packet is either an application SSL or application SSH. Once the firewall knows that these are SSL and SSH, only then it will go and check a decryption policy lookup. So it says, let me see if there is a decryption policy which wants the firewall to decrypt this traffic. If there is a decryption policy which matches, the firewall triggers the proxy mechanism. And the proxy mechanism starts right from client hello. So this client hello will now be stopped and a new client hello is created. I'm intentionally using a different color to indicate it's a new packet. Now, even though it might be a new client hello packet, we are copying a lot of information from the client hello and we are sending it. So let's say I'm sending the same 16 ciphers. Now, a firewall may choose to reduce the ciphers which it sends. That will be based on the decryption profile, but we can talk about it at the end and we'll see what all we can do with the decryption profile. So for now, the firewall is proxying a client hello with the same 16 ciphers. So in a way, if you see here, the client here is the client and the server in a way here is a proxy server. And I'm going to write that term. And if you see in this situation, because the firewall is creating a new packet, it becomes a proxy client. And PanW becomes the actual server here. Okay, so we have a client, we have a proxy server, and the proxy client will actually talk to the server. So when the server receives this packet, what it sees is that the packet is coming from the firewall. Now, the IP address or the layer 3 value of the client hello may change or may not change. So let's not get confused. When we are doing a proxy, we are doing proxy at application layer. The firewall may or may not change the layer 3 or layer 4. What I'm talking about is NATing. If the firewall is at the edge of the network, it may do the NATing, but that's not always the case. So let's say now we receive the cipher. Same logic like we talked in the SSL handshake, the firewall has to choose one of the best ciphers it wants to work on. Now, because the client request came from the firewall, the server is replying to the client, or let me call it now proxy clients. And in that server hello sh, it will select the one selected cipher. Again, the server will also send its own version of TLS and other support information there, and it will send the PanW certificate. In the PanW certificate, like we talked about, it has common name and SAN and other information. It will also send the public key as one of the attribute or one of the information inside the server certificate. Now, when this certificate reaches the firewall needs to decide something. And the decision is based on, does the firewall trust the server certificate given by the server? That decision can be made by the root certificate which is available in the certificate store. So the firewall may have the root or the intermediate into the certificate store. Basically, the firewall has to not trust. Like in the SSL handshake we have here, the client has a certificate store where the client has to figure out, does it trust the certificate from the server or not? Now, because of this decision to make, we need to create two certificates on the firewall, which will in turn sign the new certificate we create. Remember, we are doing a proxy, so we need to create a new server certificate based on the original certificate. Because once a certificate is signed, I cannot re-sign it with another CA. So I need to create a new PanW certificate. Now this certificate will be signed by so let's say we have our own root certificate here. I will call it PA root CA. And then this will have an intermediate which we'll call as trusted CA. We need also another untrusted CA. So I'm going to create another untrusted CA. The reason why we need two CAs is when the firewall trusts the certificate, then it is going to use the trusted CA to generate a new certificate and sign it with that. If the firewall does not trust the server certificate, then it's going to use the untrusted CA. Now remember, we are not using the same certificate which we received from the server. We are going to copy we are going to copy that information from the certificate like common name, SAN, and all the other information and create a new certificate. That's why I'm using a different color now, and I'm going to call it panw.com, and technically it should be a different public key, so I'm going to use just red here. Sorry, brown. Not good with colors, I guess. So we have panw.com public key with brown inside that. This certificate will now be shared with the client. So when the server, as a proxy server, or our firewall acting like a proxy server, is sending this, it will send the server hello, or SH in this case, with one selected cipher. With that cipher, it will also send the chain of the certificates here. I'm going to just write the last leaf certificate just to save some space. So let's say we have panw.com slash. So we have panw.com with public key going with it. Remember, this is not the same certificate. It's a different certificate which was created based on copied information from the original server cert. When this server certificate reaches the client, now client has panw.com with the public key. Okay, and the firewall has panw.com with the original key which we received. And like we did before, once the client receives the server certificate, it has the public key, and the client can now generate the PSK to be shared. But remember, if you're receiving panw.com, it is again a server certificate. So don't you think the client should also have something to trust the authority? So similar to what we had before, the client should also have the root CA of your firewall. Now, what if we do not have that? If we do not have that, the client would not be able to trust the certificate generated by the firewall. Okay, this is why we need to make sure that on the client's PC, if we have a cert store here, in this certificate store, we need to have the root CA or PA root CA on the certificate store of the client PC. And this is important on every client PC, otherwise the browser will give error as untrusted certificate. Now, should we import the untrusted root CA also? I don't think so, not a good idea, because then the client cannot differentiate what is trusted and what is not trusted. The idea of creating two certificate authorities here for trusted and untrusted is to take the decision making from the client of what is good or bad server to the firewall. So when the firewall is sending a trusted root CA, it means the firewall trusts this, the client is automatically trusting it. But if the firewall does not believe this is an untrusted CA, we can choose to still send the communication and let the decision be made by the client. In that case, client might be taking a risk because the firewall does not trust the certificate. Because we want the client to give an error, we don't want the certificate authority to be imported. If you import the untrusted certificate authority, then the client would again start trusting the certificates signed by the untrusted CA here. So the idea is not to do that. And that's why we always need to create two separate trusted root CA and untrusted root CA. Okay, so I just moved the untrusted CA here a little far away so that we don't get confused if this is signed by this. The arrows represents the signing here, so not to confuse with that. Now we talked about the server certificate created by the server, sent to the firewall. The firewall creates a new server certificate, or let's call it proxy server certificate, and signs it with one of its own certificate authority, depending on if the firewall trusts the server certificate or not. Now that we have received that server certificate on the client PC, the client PC can now generate a PSK. And like before, the client PC will use the public key it had before. So the client PC generate the pre-shared key, which needs to be sent to the server, but it has to be first encrypted by the public key which we receive from the server. So it will be encrypted by the server certificate. Remember, this server certificate is not the original server certificate, but from the firewall which we received as a client. Now this pre-shared key will now be sent to the firewall. So let's say PSK and encrypted by the public key. When the firewall receives this PSK, again, because we are doing a proxy, the firewall will stop this packet and trying to inspect this PSK. So when the firewall acting as a proxy server receives the PSK packet, it can decrypt this packet because it has the corresponding private key on the firewall because we created that server certificate. And then we can now see the PSK, which was again created by the client there. The firewall acts as a proxy server, but also a proxy client. We are not the actual server. So we need to send the PSK packet to the server as well. Now we can create a new PSK. So let's call it PSK2. And this PSK2 will be now shared with the original or the final destination. And again, we have received a certificate. This panw.com with the green public key in a way was the original server certificate which the firewall received. We are going to encrypt the PSK with that and then send this PSK to the original server here. Same logic. When the server, oh, I forgot the 2 here. When the server receives this PSK2, which is encrypted by its own public key shared in the server hello, it is going to now decrypt it. So I'm going to use the same red color. Even though I'm using the same red color, they're not the same private keys. They're different. We decrypt it and we then get the PSK2 here. Now we have a PSK1 available on the client. We have a PSK1 available on the proxy server. We have a PSK2, which is let me write that here. We have a PSK2 available on the firewall and we have a PSK2 available on the final server. Next thing we do is to calculate the master secret key like we did before. So I'm going to use the PSK and other informations of ciphers to calculate the master secret key or the MSK. This master secret key, remember, like we discussed, does not get exchanged. It has to be calculated individually by both of them, client and the server. So I'm going to use purple for the MSK calculated by the client and the proxy server, and I'm going to use maroon color, I believe, and we are going to again calculate MSK on the firewall and the server, and let me again make this as MSK2. What we're trying to understand here is that the MSK or the master secret key is not exchanged and calculated individually by the client and the server. So now that we have the MSK on the client and on the firewalls, there are 2 MSKs here, and on the actual server, what is the MSK used for? If you remember what we did in the SSL handshake here, we use the MSKs to do the encryption and decryption now. So this is the final key which will be used to do both encryption and decryption. And that's what we're going to do. So let's say this green is again data. I don't have more colors. So let's say we have a data we want to send here. Again, we want to send this data securely to the server. So I'm going to encrypt this data. Okay, so let's call it encryption. We are encrypting it here. So now let's say the client wants to send some data, and let's say this data is the HTTP GET, assuming this is a web traffic, so we want to send some data. When this data needs to be sent, so let's use the same data here, and we call it data, and this data is being encrypted by the MSK1, which is this color. When this data is received here, the MSK1, which was calculated before, can be again used to decrypt it. So I'm going to decrypt this packet and get the actual data. This data is important to the firewall because this will be used to figure out URL categories, to understand the applications which are going through the firewall in order to decide if we want to allow that packet to go through the firewall. Let's say the firewall wants to allow this data. We are now going to use the MSK2, which was basically created between the firewall and the actual server. So again, there is a communication for that. So we have data, and this data is now encrypted by the MSK2. When we receive the data here, the actual server will use the MSK to decrypt it and get the final data. So if you see in a summary, the data which was created by the client, it went to the server through another encryption. The server decrypts it, reads the information, encrypts it again with a new or a separate MSK, sends it encrypted, and the final destination will receive this data and decrypt it with the MSK2 here. And this, in a way, if you understand, they're technically two SSL tunnels. So let's talk about the data going through. So when the traffic goes through, there is an encrypted channel here. So this is technically everything. Let me use the same color to indicate that. So this is technically encrypted here, everything between the client and the firewall. And there is another encryption, which I'm going to use a different color here, between the firewall and the actual server. But in the middle section just is basically the clear text. We have an encryption between the client and the firewall, and we have another encryption between the firewall and the actual server, but there is a clear text in the center. This clear text will be the same data which we see here, which is clear text. Because when the client is creating that data is clear text, it gets encrypted, gets decrypted, then we have a clear text, then it again gets encrypted, then again gets decrypted, and then we get the clear text here as well. So the dotted lines was basically to represent that on the client, on the firewall, and on the server, the data is clear text, but everything in between is encrypted. And there are two channels of encryption happening here for the forward proxy.
Cool. I'm learning a ton. Yeah, well, you're a great teacher, so thank you. Thank you for watching this episode of Learning Happy Hour. At Palo Alto Networks, we are strong advocates of continuous learning, and we hope you are too. To continue learning about our fantastic products and services, you can attend a class with one of our authorized training centers, or you can self-study about these products and services through our digital e-learning courses. And if you like this episode of Learning Happy Hour, consider watching this one or this one, and don't forget to like, subscribe, and share with your friends. And thanks again for watching.